Welcome to this Passive Social. It's part of the In the House series we've been running, in my opinion, for way too long. Unfortunately, COVID is forcing us into this space, but we're still making the best of it. Of course, we want to thank our sponsor, SIGA. Andrew's here, and they've been very loyal to Passive Canada on this process, and we appreciate it. And also acknowledge that these are developed in partnership with Zebex. So I think that has dropped my sharing results. So we are here to talk about the Little Mountain co-housing project. And specifically today we have Sandra Roller from Project Architect from Cornerstone Architecture. And then we have Einar Helbig, Managing Partner, and Travis Burden, the project manager from E2 Group. This presentation is intended to, the project's currently being built, and it is intending to we set it up as a bit of a problem-solving exercise. They've got an interesting building that needs to do an air test, and they've gone through a number of the preliminary reports. So we started to create a video, and they're going to build a presentation up on that story with a bit of background on the project. So with that, I will stop my share and hand it over to Sandra, Travis, and Einar.
All right. Let me share my screen. Maybe I should say a few words first. So the way we set this presentation up is that since we're focusing really on prepping the building for airtightness, I could talk about this building for days, but I figured I'd just give you a brief background. So I have a fairly quick slideshow on the backgrounds of the building, on the layouts and the challenges, and how the design came together. And then we have produced a little video clip where we are going through the building and basically do the air tightness prep walkthrough with Travis and Einar from E3 Eco Group. So I think without further ado, I should figure this out now. Now comes the part where co-housing project. So Little Mountain co-housing is a project, passive house project, obviously 25 suites, large amenity spaces, a guest suite, and common workspace. Location in Vancouver is in the Little Mountain area, right there. You can see, can you guys see my mouse?
Yeah.
Yeah, no? Okay, so you've got Main Street here, this is 33rd, and Quebec Street is right here. This is the Hillcrest Community Center, this is Queen Elizabeth Park. So that's the location. So in terms of design, few things that influence the design. Oh, I should probably say at this point in time that I cannot take credit for the actual design of the building. That was Scott Kennedy and Simon Richards from Cornerstone. They designed the building. I came in at prior to stage to, as I jokingly say, make this building a passive house, which is not entirely true. Anyway, so the design process was, because it's a co-housing project, which is not to be confused with co-op housing. So co-housing means you have owners that form the development company, and then they basically hire the consultants, architects, and the project manager to channel all, in this case, 25 owners, 50 people's wishes to build their own home. The other interesting part was obviously, as we always know, design guidelines by the City of Vancouver don't always help the case of passive house, let's put it that way. Setback requirements are not always helping, whereas we try to develop a compact building. So we've all seen this slide, so I'm not gonna actually talk too much about it, but it is somewhat important as we go further through the design process. So we know as we go away from compactness, our building has more heat loss area in comparison to the floor area. So then there are rezoning policies. This entire Little Mountain area was rezoned to 6-story multi-residential buildings in wood frame construction to make it affordable. And then obviously the typical design guidelines. The city actually called it once the Main Street Character Design Guidelines, whatever that exactly means, but we're asking for setbacks and these kind of things. So here's the site, schematic design site, building envelope. Let's go through this a bit quicker. And then we had the first concept section. So there is zoning asked for the streets facing, for the suites or units facing Quebec Street to have exterior access, so have access to the street. So there was basically the idea of having townhouses on the bottom. And then what you always find in co-housing projects, as it is a community of people that comes together first, so they actually want common areas, right? They want to actually have areas where they can spend time together, but also have their own units. So every co-housing project has a so-called common house, which is a larger amenity space with a larger kitchen, not a commercial grade kitchen, but a big kitchen where they can all gather together. And then we'll see later in the floor plans that there are other communal spaces in this building. So compact, 6 stories. So this was it. So here's kind of, I think from what I understood is there was a bit of a two designs. So initially the design was fairly compact with a few setbacks here and there, which had to happen. But then there was this very strong, this is from the back, there was this very strong wish by the community, and I'm going through this quicker, to actually create a communal backyard where they have, like, as many units as possible have a visual connection to that area, right? And so this is now the view from the lane. This was the view from the front. This is Quebec Street, view from the lane. And this is basically the way the building looks right now. This was still schematic design, but what we have here is a U-shaped building. So we did add quite a lot of heat loss surface, to speak in passive house terms, to make this desired building shape, which is working really well, work. So you can see here, we have an exterior staircase, which you will see later, but we also have these exterior pathways on every single level. And that those, including the balconies, allow this visual connection to this backyard. And down here, we've got this amenity room spilling out into the garden. Here's a kid's playroom going into the garden. So now this was the start of the schematic design. And this is how the building actually looks like. So you can see here, that's the courtyard with the exterior staircase. I've got some floor plans that show that a bit better. So that's a site plan, not really important at this point. Parkade, obviously there's underground parking, which actually has a music room and a bike room in there also, different from normal developments, like a bike repair room. It's a workshop. And so now this is the main floor plan. You can see here, I hope it's visible or legible. This is the parkade entry. This is Quebec Street. So here's the main entry. You go in here And then this is the very, very large amenity space with the large amenity kitchen, right? There is a communal washroom down here, mechanical elevator, but then there is another amenity lounge. So also this whole downstairs area is all communal, and this one kind of goes out straight into this big garden area. Then here you go through here, and this is our exterior staircase, right? So that goes all the way up to the roof deck. And then you go back in here, and there's a communal laundry room. Even though all the units have their own in-suite laundry, they still wanted communal laundry as another option. And this is the children's playroom, again, with direct access to the outside here. These four ones here in the front, those are the four townhouses. They all have an entry from the street. And those are the only two units in this development that are actually 2 stories. So as you go up, you can see here, these are the townhouses up here. This is a 1-bedroom suite. These are 2 2-bedroom units. And I believe those ones are actually the only ones that are stacked all the way up. Everything else changes on every floor, somewhat slightly, but still it changes. So we have 25 units and 13 different layouts. Here you can see that exterior staircase and those connecting pathways on the exterior. So on one side, they enter into a unit, and on the other side, they actually enter into this hallway that then enters into the units on every single floor. So I go up, up, up. And this is where we're getting to the 6th level, where we have our setbacks, big open roof decks, another fairly large common room up here, so another amenity space. Actually, I forgot to mention, on the lower levels down here, there is one space which is a guest suite that can be used by anyone who has guests over, with its own bathroom. And then on another level, there is another common room, which is a common workspace. And this is the roof deck with garden beds. So the elevator goes all the way up, the staircases both go all the way up. So this staircase is actually entirely exterior. This one does not go down into the parquet, this one does, and so does the elevator. So this is basically the design of the building. Now, what this did, and we need to focus or not emphasize on that. You can see that the heat loss form factor on this building is 1.72, whereas on a building like, let's say, the Heights, which is at Skeena, Cornerstone's first passive house building in Vancouver, probably the first passive house building in Vancouver in multi-residential, has a form factor of 1.12, which is fairly compact. So as we know, design of continuous air barrier is a large challenge. So we looked at different wall types, and we basically looked at this and this, and this one is not ideal in building science terms. This one was too costly with the rock wool on the exterior, which right now we're looking at again for a different project, because lumber prices are so high that this one might actually be less expensive than the chosen one that we used for Little Mountain, which is this one. It is what we used on the Heights. But because of the form factor being different, the EPS layer had to be 1 inch thicker, which is quite a bit for the entire building. Now this is the sequence. You can see here, exterior wall, interior wall. We left this part open when we put it together because we had to fill this in after, right? So that's how it was put together. Then there's the exterior, the membrane, we call that the floppy bit, the MyVest that needs to go on first so we can wrap it around after, right? So here it comes up, and then there's the next one. Pretty straightforward building assembly. The windows came in. Then we have our first layer of bad insulation. And now comes the quick therm. And now here with the quick therm, you can see it is actually taped. So the foil-faced part of the quick therm insulation taped is our air and vapor barrier on this project. So it kind of connects to the MyVest up here, and then the MyVest goes around and ties back into the next wall up there on the next level. And then comes the service cavity after, which is filled with bad insulation again. These interior walls are partly filled just for sound insulation towards the rooms with the HRVs in them. Then the other challenge we faced on this building was that because of its layout and its shape, there were some challenges to get it seismically and structurally stable. So we unfortunately ended up with quite a bit of additional concrete on the main floor. And that is right here. So initially all of this was wood frame construction. And then right after tender, we added some structural concrete here and also some more shear walls down here. So you can see, I thought I had some photos. Oh, there's something coming up, yeah. So actually, that was supposed to be somewhere else. I think I screwed that up. The order of the pictures is wrong. Doesn't matter, I can talk about it anyway. So these were some typical details where we had to kind of come up with a solution. This is what we did initially. And then you can see here, we cantilevered the wall type. Or the frame wall to kind of make this insulation part just a bit continuous, right? And so we had monoglass. This is the parquet. So we had monoglass on the underside of the parquet, but we changed that after to this kind of assembly because in this case, so we added this little concrete upstand. And we kind of we lifted this one up a bit so that part is now our continuous insulation. So that made it easier for us to address those thermal bridges. We still kept the monoglass, but it's instead of 10 inches here, it's now 5 inches there. So we basically sandwiched the floor, which helped with eliminating other thermal bridges like the columns in the parquet that would come up here somewhere. So with this continuous insulation on the upper part, we were able to address that nicely. You can see here how it's built now. This is on the outside of the main floor. This building has actually in the end being built as a prefab construction, which was not always clear from the beginning. Ideally, it's good to know when you actually do the construction documents and the drawings, whether or not it's being built like this. So here's the same thing. This is the concrete wall now that was put in later that we had to kind of address. So again, this was our initial design, and then we changed it to this one, which kind of makes it better for eliminating thermal bridges. Yeah, so here's our full-on concrete ground floor, which was one of the few buildings, because it doesn't have a commercial component on the ground floor, wasn't actually necessary to have in concrete, but for fire rating reasons, but it ended up being concrete for structural reasons. Now, in terms of thermal bridging, don't want to spend too much time on this, but obviously we all know that we ended up on this project with quite a few that had to be calculated, and Lindsay from our office did an awesome job on illustrating this and putting it into the PHP right after. So I'm going through, yeah, here's some other challenges we had. So initially, this is the second story now. Again, cantilever here. This is the parkade entry ramp. Some continuity of insulation achieved here by cantilevering the wall, the frame wall. That was all reviewed and structurally supposed to be okay, but then when it went into construction, the hold down engineer said that that doesn't work, so we had to kind of add on this little ledger. It's all not a big deal, but obviously I'm just telling what we went through with this project. So this is how it now looks like. So I think the thermal bridge hasn't gotten any, well, it's a bit, but it's not a lot. So that's all fine. And there's some other calculations we came up with. Oh, this was an interesting one. For whatever reason, we ended up with a toilet over a cantilevered open space. So there's a washroom here. So again, because it has to drain somewhere and it can't just go straight down, we had to basically add on this package of insulation to make this work down here. And there are some other things here, thermal bridging. So it was a fairly, I would say it's a fairly complicated building with a lot of details that needed a lot of attention. But as a pretty good team, we made it work, I believe. So in terms of windows, the windows we started looking at initially in our model was Euroline, mainly because they are somewhat semi-local, being manufactured here with imported profiles, and we've used them on Skeena, so it seemed like a good idea. And then later on, we kind of decided for others. So in terms of thermal bridges of installation, this is kind of the detail. Again, it's a fairly similar detail that we used on Skeena. And the reason here is, again, as most of us know, I saw who is in the audience, we all know the window ideally shouldn't be here, it should be here, right? Center line of the insulated wall. Now, we were able, I can use this one too, we were able to make the model work having it here. And what this did, it obviously, you can tell, achieving the air tightness out here was so much easier than having the window set back. Yeah, so these are our actual details that we ended up using. They have a little bit of an inset here to have the interior shading. I'm going to flip through this a bit faster because it's really not that interesting right now. These are the windows we ended up using, not Passive House certified windows, but as we all know, they don't have to be certified. They did provide all the parameters that we required for this project. And they are wood on the inside and aluminum on the outside, which is a fairly nice feel. And they were price competitive, and they are installed now, and they're quite beautiful. So in terms of the ventilation system, and this is where it gets more interesting again, we are using Zehnder ComfoAir 200s, one per apartment. So every single unit, because it's a condo building after all, every single unit is owned, it's not a rental building. We decided to go with a decentralized system for the units, so they all have their own ComfoAir 200s, which again now becomes interesting when we think about prepping the building for air tightness, for the air tightness test. So you can see here the components. This is the silencer. sorry, I don't want to spend too much time on this. I just feel that most of you know these components by now, and we really wanted to talk about airtightness. So maybe this is an interesting one. We're using this Rezoning exhaust and intake grill for our units. So you see those on the exterior of the building. We're using these ones for the common rooms. I think we have one Comfort Air 350 and two 550s for the common rooms. These are the Hiv layout plans that that we actually did. So we did the Hiv layout plans, and I think I've zoomed into some here. So we produced those basically figuring out in which cases we kind of coordinated that with the structural plans. So there are some with dropped ceilings, and the dropped ceilings are lower here because the Hiv needs more clearance than the other dropped ceilings. But then we also have areas where we don't need dropped ceilings because we're running those in the joist spaces. This is the intake and exhaust, Hiv here, silencers here, and then we basically ended up drawing like all these little comfort pipes to the intake and exhaust in the rooms. You can see that here. Here's another one. So we did that for every single unit. There was a bit of a coordination, especially with structural, but it worked out well, I would say. Yeah, so these are our ventilation plans. It goes up. Yeah. And then domestic hot water on this project, we are actually, well, we did a bit of investigation in different kinds of strategies, but then we ended up using 4 Sandon heat pumps on this project. Initially with an electrical backup, but then at some point we felt like we're confident enough that we don't need the electrical backup tank. So this is how the hot water is generated. The other thing we investigated and almost got it approved, we did get it approved, then it was revoked, was air admittance valves on this project and the papas, which are the, oh God, I forgot what it's actually spelled out, pressure attenuators that go together with the papas. And that is basically to reduce the heat loss through the plumbing vents, right? It is quite substantial. And so the idea was to use AAVs everywhere in the building and basically not have any roof penetration for the vent stacks, which is common practice in other parts of the world, but hasn't totally been approved here yet, other than for island sinks. So the idea here is traditional system would have been, we all know this one, venting pipe goes through the roof, right? This is the building enclosure. And what we had proposed initially was AAVs at every single fixture. And then also an AAV on the inside under the roof on the top of every single plumbing stack. So we had a lot of back and forth with the city on that one. Yeah, you can see that here too. So this is basically all on the inside, nothing goes through other than the city vent, the city sewer ventilation that had to go over the roof. So what we were asked to do by the city is basically recreate scenarios where we would use what we wanted to use. And you can see with the AAVs, we were at 13.9 heating demand. Without them, we were at 16.3. And then they asked us, so what would it do to your wall assembly if you wanted to achieve the 13.9 without the AAVs? So it turns out we had to actually add another 5 inches of additional EPS, which obviously wasn't an option. So, and this was the other thing they asked us to do. show us what would happen to your roof deck, which was planned without the plumbing stacks coming through. So it would have looked a bit like a Swiss cheese, because these would have been all the spots where the plumbing stacks would have come out. Long story short, initially they said, yeah, we could do that, but then there were some second thoughts, and then what we ended up doing was I don't know, there's a slide of this. We actually ended up having...
Okay, Troy, don't mind. What the fuck?
What's happening? All good? Okay. Air admittance valve. So plumbing stacks bundled and 4 penetrations, and we now have the air admittance valves 1 meter over the rooftop outside, which basically still kind of stops the continuous heat flow. Yeah. This is where, and now this is kind of where it all ties back together, and I think we're almost here at the end. This is where our current PHPP sits, yeah, which is why our air tightness test is so important to turn out good. Yeah, I think that's basically it. We use the design pH to actually model the building, and I think, unless there are any more questions, I think that's it for the intro of the building itself. I'm happy to share more construction photos later, but I think that can come up during the discussion if required.
I'd love to know the reason, Chris, Sandra, why all of a sudden at the last minute or whatever, the city kind of revoked their AAV approval. Like what specifically? I'm not
Yeah,
sure
there were some further discussions, and didn't feel quite comfortable with. It's all about, I think, from what I understood is, I mean, it's all about life safety, right? And so there was a bit of a concern that if those AAVs fail, and nobody ever heard that an AAV fails, that ventilation would not be working properly, right? And so it's kind of, whereas I feel with a continuous ventilation system going, the concern wasn't totally valid, but they muted you again, so you can't really, we can't have that discussion with you right now, but I'm gonna share my screen, and then we should watch that movie first.
I muted myself.
Oh, you did? Nice. All right.
It's very unpredictable, and we ended up actually exactly where I thought we would end up with, which is a standard ventilation system,
Yeah.
retrofitting an air admittance valve on the top. And interestingly enough, the air admittance valve people would like to have seen us put what they call a papa in the system, but then the city wouldn't permit the papa. So we got the worst of everything. That's what we got. But at least we got AAVs, so that's better than not.
That's one step on the road to getting all the way there. Hello everyone. My name is Sandra Roller. I'm with Cornerstone Architecture, and we are here today with E3 Eco Group to do our pre-air tightness walkthrough on our Little Mountain co-housing project in Vancouver. And we will talk a bit about the building, but we'll mainly talk about different approaches of how to prepare the building for the air tightness test. And I think with that, I'll just hand it over to Aina at E3 Eco Group.
Great, thanks Sandra, thanks for having us out. Travis and I are from E3 Eco Group, and we were asked by Sandra to come down and talk a bit about this building in terms of how the air tightness test is going to happen on it. So Travis and I are going to talk about two categories of preparation. One, the building as a whole, and then we'll see later on that there's an extra added element to this particular building because there are some separate units that have their own exterior entrances. So not every part of this building is interconnected. So that'll add some complication to it. It's a good example that we're able to show here on how the building gets prepped. So while we're outside, let's talk a little bit about the overall concept. So you can see the building in the background. The purpose of the air tightness test is to find out how airtight the building envelope is. So what that means is we want to be able to test the envelope as a whole. So that will relate back to the complications with these separate units and separate entrances. We're going to end up testing this building with our blower fan equipment that probably everyone watching this video has seen, at least for a house. Same approach, but we're going to use multiple fans. You might need 2, 3, maybe even 4 fans, depending on what kind of leakage numbers we get. Obviously, this being a passive house building, we should need even fewer fans than if it were a typical building not meeting the passive house standards. So we're going to talk about the overall building prep, and then we're going to go inside and we're going to talk about how we prep some of these units that have the exterior entrances.
Okay, so for this type of building, it's a passive house building. So we'll be testing this building in accordance with EN 13829, which is the passive house testing standard. So in order to do this type of building, we're actually going to be locating a blower fan at the entranceway of this doorway behind us here, and we're going to be pressurizing, depressurizing and pressurizing this building to at least 50 pascals, and after that we'll take the results of both those tests, put them together and get an average, and we'll be targeting a total of 0.6 ACH, which is air changes per hour. So this is a very tight metric, so this is something that we have to keep in mind when we're prepping the building. So there's certain things that we want to make sure that we account for, such as leakage to the exterior of the building or infiltration. So some of those items include things that we'd be stealing from the exterior of the building. So I'll get Ina to just talk us through some of the locations of those exterior penetrations that we can see.
So Travis is absolutely right. We have to be very careful that we're making sure we're following the appropriate testing standards. That means for this building, we have to understand it's going through passive house. It has a particular air tightness target, 0.6 air changes per hour, 50 pascals. And we have to understand the ins and outs of the particular testing standard, EN 1382. So in terms of preparing the building, it means that things like the ventilation ductwork that's up there, you can see poking through the inner side of the balcony system there, those types of penetrations are designed to be there to carry the ventilation there, air through in and out of the building. So the testing standard allows those to be sealed off for the purpose of the testing. That's pretty typical for other testing standards. The idea is to test the air barrier system of the building and not include dedicated air going in and out for ventilation. So those are sealed off. So that means that as testers, we have to know what penetrations can be sealed and what can't be sealed. We have to work with the site staff to give them a list of things that have to be prepared in the building, which is quite a lot of work. There's a whole bunch of those penetrations all over the building. Some are accessible from the exterior, some are more easily accessible from the interior, which we'll show on the inside. There's other ventilation penetrations, like an elevator shaft usually has a vent up the top. Sometimes mechanical systems have if the gas system, there's a air exhaust and air intake for the combustion system. So we have to know what's involved, and we have to give instructions to the site staff to prepare the building. Why the site staff? We recommend that. In fact, we typically recommend the mechanical contractor for the building be either the ones or heavily involved in preparing the building, because typically these penetrations have to do with mechanical ventilation, maybe heating or cooling. So it's the mechanical contractor that we feel is the best able to know where all those penetrations are, and also turn off any fans in combination with sealing off the ductwork so there's no issue. And then when the building is finished testing, that's the right person to reactivate the mechanical equipment as they take off all the sealing as well. We kind of look at the building prep and the whole testing process kind of like painting. It's a lot of prep work, and the actual testing really comes down to maybe half a day's worth of work. You might have 2 or 3 days worth of work to prepare the building ahead of time. So that's a little bit of the situation from the outside. It's all about testing the envelope and not including the dedicated ventilation or other air ducts that go through the building. So those have to be addressed, those have to be sealed up, and also making sure we're testing to the right standard.
So as Anna just stated, ideally we are air testing the building as one volume. One challenge with this design is that we have those exterior walkways accessing every level, and we have an exterior staircase. So that leads to the fact that our building is actually not one volume, and we have discussed a few different approaches.
Based on the design of the building, as Sandra said, it's not all one interconnected volume. That is the ideal case for us to test the building. We would want to be able to test the entire envelope in one test without having to separate different things, because that introduces the potential for error. However, this building is not one interconnected space. As Sandra said, this bank over here, these are separate levels of different units that have their own exterior entrance off of these balconies you can see in the background. So these units have a separate entrance, and they are not internally connected to the rest of the volume of the building. We can test all this volume of building over here on the left, but we can't automatically include these units over here on the right. So a couple of different options that we've come up with. We had some of our own ideas, and the site staff, actually, the builder, had another option as well. So there's three potential ways it could be done. One way is we could test the large volume over here on the left, as we normally would, get the result there. And then we could put a fan in each of these individual units and test them separately, and then add up all the results together. Challenge with that is there probably will be some leakage through the party walls and through the demising floors, because they're typically not perfectly airtight. So if we tested everything separately, added all the numbers together, we'd probably overestimate the envelope leakage. So we could do a variation of that. We could bring enough fans, put a fan in all the separate units, run them all simultaneously, and then that would pressure balance the party walls and the demising floors, and we'd probably get a better result there. But having all these fans running, we need something like 6 or 7 fans all working together. That's not a perfect solution either, because there'll be some errors introduced with that. Another way to test it is to potentially look at some ductwork of some sort, connecting the entrances of these separate units here to the main part of the building. So there's a pass-through, and as we depressurize and pressurize the main part of the building, air can flow through this connecting ductwork and connect the smaller spaces, the smaller separate spaces, into the larger part of the building. As you can imagine, that adds some complication of who's going to install this temporary ductwork, how big does it need to be, how do you make sure it's air sealed into the doors, that type of thing. So that's another potential option, maybe not the ideal either. Another way it could be done, which is probably how we're leaning towards for this building, is we'll work with the builders to introduce a hole in the walls that are separating these individual units from the rest of the building. So that way there'll be a pass-through for air to travel from these units to the main part of the building as we pressurize and depressurize the main part of the building. And that will probably be the best way for us to get the most accurate testing results on the whole building. Of course, it's not a perfect solution because it introduces a bunch of additional work for the builder. The builder's going to have to need to cut a hole in these party walls for the purpose of testing, and then patch that hole afterwards. So again, not a perfect solution, but there's a few different options that a building this can be approached that we've come up with. Maybe there's a better solution somewhere we're not aware of. But for this building right now, we're leaning towards asking the builder to kindly leave us a hole in the party walls so that air can pass through between the separate units into the main part of the building. And that's what we're thinking we'll do to approach this building for testing. So here we are, a little close-up view of the idea, the issue the challenge we just talked about a minute ago. So over here, this is the main part of the building. All these units and these levels are all interconnected. This is easy for us to pressurize and depressurize this part of the building with our equipment. The challenge here is this unit. This doorway leads into a separate unit. There's a party wall running into the building over here. So this big part of the building is not connected inside to this unit here. But we want to test all those spaces together. So one of the options we had talked about is literally running some ductwork between this doorway here and this doorway to connect the spaces. So you can imagine ductwork running through here. We have a large diameter flex duct that could be used for that. We would seal up the openings, both doorways, with either plywood with a hole cut in for the ductwork, or we'd use some of our extra blower fan equipment. That is a potential way for us to pressurize and depressurize this part of the building and include the air leakage through that connecting ductwork for this space. So again, it's an option. One of the options we talked about earlier, again, to try and make sure we capture with the same test what's going on there for leakage as we capture this part of the leakage here. Now we'd have to do that for not just this floor, but the other floors are going, there's 6 altogether?
Yeah.
So there's 6, there have to be 6 of these connections. If there was only one, we probably would do this, and it'd be a really good way to capture this unit over here. But because there's 6, it gets a bit more complicated, and that's another reason we're leaning towards these air passages in the party walls, which we'll take a look at from the inside. Down here. So now we're inside this ground floor unit that is separated from the rest of the building. You kind of get a bit of a sense with the camera walking in the unit. You can see the party wall over there. In this case, it's a shear wall, so it adds a little bit more complication to it in terms of an air pass through. But you can also see from this perspective that this space is not connected to the rest of the building. Okay, so again, our suggestion is to literally ask the site crews to cut a hole in here, and size-wise, it has to be big enough just to make sure that air can be easily drawn out of this unit into the rest of the building. The rest of the building is just on the other side of this party wall here. So we're thinking it's going to be something like a 2-foot by 2-foot hole, which is actually pretty good size hole, but we're thinking roughly that size so that there's more than adequate air flowing out of here, and it won't cause any negative effects to our testing. And again, the purpose for going to that length, if you will, of cutting some temporary holes in the party walls is so we have the best chance to get the whole building airtightness number correct. Particularly important because this is a passive house, so we all know it's got to be super tight. We don't want to risk any testing procedure that might give inaccurate results, especially if those results add to the air tightness. So here's an example of one of those party walls. We might look at some others later in the building here, where we're literally envisioning a roughly 2-foot by 2-foot hole here, so air can pass through from this unit into the rest of the building to make sure everything gets tested all together.
Okay, we have an in-suite HRV ventilation system here. So we have a Zender system here. So what Ina had mentioned at the start, there's options to seal these. These will have to be sealed during the testing procedure. So there's 3 sort of ways we can seal this sort of system. The first, which I had mentioned, was sealing from the exterior vents. So in these systems, they have an intake and an exhaust port, which comes to the exterior of the building. So this would be our primary option for sealing. To seal on the exterior of the building at the weatherproof cowls there. The second option to that would be actually sealing on the inside or on the intake of the HRV system itself. So in here you can see the ductwork is actually exposed here. You could actually seal those from the exterior of the HRV or on the inside there. And then thirdly, we would actually be looking at following this ductwork down and sealing from the grill terminal itself on the face of the grill terminal. Now, the pros and cons of this sort of style of sealing is if we were to seal at the face of the grill here, we can introduce any of the duct leakage that occurs in the duct run back to the exterior of the building. So that's for that reason, we always recommend sealing at the exterior of the building as a primary technique to seal an HRV ventilation system. Okay, here we have the below grade vestibule. So behind us here we have the parquet, and I have the elevator shaft behind myself here. So at this location here, we're actually going to have a passive house door sealing off. So at the time of testing, this area behind me will actually be included in the building volume that we're testing. So this space behind this door will be unconditioned space, and this space here will actually be conditioned from a rooftop HRV hallway pressurization system. So what does that mean for the purpose of testing? At the time of testing, obviously this door that's going to be located here will have to be closed and sealed. The elevator shaft behind me here would have to make sure that any sumps or drains at the bottom of the elevator shaft will need to be primed to make sure that they are fully sealed. And then when we go up the elevator shaft to the rooftop, we want to make sure that HRV system servicing the vestibule and any of the hallways throughout the building is also sealed. And again, we want to seal that primarily from the exterior vents on the intakes and exhaust ports for the HRV system. Okay, so as we mentioned below in the below grade vestibule area there, we had a rooftop HRV unit which is going to be servicing the entire building to provide hallway pressurization. This is one of the grill outlets for that mechanical duct riser here. So this is another one of those options where you could seal this system at the face of the grill here, all throughout the building as we go down the building. However, again, as we recommend, the best way to eliminate any included duct leakage into our air leakage test is to seal that unit from the exterior, which we'll see when we go up into the rooftop. Okay, behind us we're going to have the future location for the kitchen hood. So typically when we would test a regular building that's not a passive house, we would see ducting from this kitchen hood going to the exterior of the building. Now, being the fact that this is a passive house, they are required to have charcoal filters in their kitchen hoods. So the system basically recirculates into the suite. So there isn't any need to seal the kitchen hood itself because there is no exterior ductwork for this. And also, when we go over to the future location for the drying system, there is no cutout for any ductwork in here because I'll be using a condensing dryer. So this is also a passive house specific appliance, and there won't be any external ductwork needed for that drying system. Perfect. So I guess I'll just jump to some of these floor plans here. This was something that we were looking at on level 2. So in that video there, Ida was standing in this area on the ground floor actually, which is the open space between the two building interior spaces. So what our problem was when we were looking at setting up our fans and interconnecting all of the spaces in the building so we can run the test as one, is that there is these partition walls on the second floor, and then as we go up through the building, this space over here is completely separated from this space here with no interconnecting spaces or doorways or any hallways or anything. There's only this external staircase which runs up the building with 2 door entryways here. So the first I guess the three sort of options that we explored throughout this was, firstly was, which was a suggestion that we had from the construction team, was to actually set up a blower door in each blower door frame in each of these door frames here, and then have a piece of ductwork, like expandable, flexible ductwork connecting between each walkway between each suite. So there'd be 5 or 6 of these running up on each level as we go up the building. And this option is totally viable, but again, the problem with this is the amount of door frames that we'd have to set up and the amount of ductwork that's introduced can introduce a lot of unintended air leakage into the test results. So for this reason, we recommended against this option. The second option, which Ina mentioned, was literally running individual fans for each of these areas. So we'd have a fan in this doorway here. We would have one fan on the entranceway here, which would actually carry through the whole large area of the building all the way up through the stairwells and elevator shafts to the top floor. But we'd have to have individual fans for each of the spaces here on every single floor. So you're talking 5 to 6 fans with a test running all of those pieces of equipment simultaneously. And again, it can introduce errors or additional leakage into our tests that it can add extra infiltration into our test that we don't really want to account for between the demising walls. So that's why our primary option, which was sort of laid out here, was to cut in some penetrations through the drywall here to create continuous air paths for the fan pressurization, depressurization to travel through the building. So
I'll add in a comment there if I could, Travis.
Yeah, please.
About the second option you just described of having a separate fan in each of those separate spaces and running them all together. Probably at least some of you have heard of that before, doing a pressure balance testing. And so we found the theory is great, but in reality, the practice doesn't work perfectly. And Travis said exactly the right thing, which always makes us nervous, is what's the risk that you're introducing more potential for error when you have not just additional fans, but the fact you get separate fans in separate spaces and you're trying to coordinate everything together. You need one operator per fan in most cases to make that work. And we have a lot of experience doing pressure balance testing with row houses, side-by-side row houses. And it's actually very interesting and a little bit shocking sometimes to do an air leakage inventory while we're supposedly pressure balancing these row house units, and you're still finding that there's air coming in where you wouldn't expect it. So obviously something's not like perfectly, not working perfectly despite our best efforts to do pressure balancing. And of course, applying that to this building, we know that this building needs to hit a very aggressive air tightness target. So we really want to come up with a testing strategy that minimizes the potential for error in the testing process.
Yes, thank you, Anna. Yeah, and that's why of the 3 options, we did decide on the primary option to remove sections of the drywall or create penetration through the drywall for airflow to pass through. Because when we're doing this mode of testing, we are literally just running 1 or 2 fans from the entryway of the building, and we are testing the building envelope as a whole. And we're not going to be testing any of our results won't capture any of the leakage through any of the internal partitions. So the airflow would be coming in through the doorway here, up through the staircases to the floors above, or up through the elevator shaft into the lobbies. And actually, why I mentioned that, this is also something that's worthwhile mentioning. part of our testing boundary, which is outlined here in the red, will include this parkade level lobby in here. So this actually, you know, we are including the stairwells in the test, and we are including the elevator shaft as part of the test. So in this particular layout, there is going to be a passive house door here. This is going out to the parkade, and another passive house door here into, I believe it's like a bike storage area. So these are all unconditioned spaces. These aren't part of the air barrier testing boundary for the purpose of the test. Everything on the inside here is. So when we look at something, say a elevator shaft, we're assuming that airflow is going to be filling up that elevator shaft. So we need to make sure that the bottom of the shaft is sealed. You know, if there's any drainage or sumps or anything like that on the bottom of the elevator shaft, that needs to be primed or sealed. And then for the purpose of this building, it actually has, for the hallway pressurization, it has a rooftop HRV system servicing the entire building. So this is actually servicing, it'll be coming, airflow for that would be coming through the elevator shaft, stairwells, everywhere through the lobbies and every single floor. So that's an additional piece of like shared mechanical equipment that would need to be sealed, as well as the in-suite individual HRV systems. So when we work our way out the building, we can see, we expect that airflow to come up through the stairwells here. We've created proposed locations for the airflow to travel through the demising walls here and into each suite. We want the pressure in each suite and throughout the building to be relatively equal at the point of testing. So in order to get the building ready for the day of testing, we have to prep the building. So one of the main things that we look at, well, I don't know if we mentioned this in the actual part of the video, but what we certainly look to do is to include the construction staff and also additionally the mechanical contractor for the purposes of sealing. I think it's very...
Sorry, let me interrupt for a second.
Yeah.
Would you mind, I'm assuming everybody sees the same thing I'm seeing. Would you mind just maybe closing your display on the left and right so we can and zoom in on the body of the report here, please? I think it'll be easier to follow. I'm also noticing like there's a delay between when you move your cursor around and when we see it. So that's challenging to follow. So just be mindful of that. And yeah, so we can sort of follow what you're saying a bit better, please. Thank you.
Yeah, absolutely.
Thanks.
So, okay, I'll move down to this portion of the test here. So this is, like I mentioned before, about creating a pathway for the air to travel throughout the building. So for the purpose of the testing, we need to make sure that all the interconnected spaces are open, doors are propped open, future locations for passive house doors in that below grade vestibule area are going to be closed so that they're excluding any unconditioned spaces. The elevator shaft is closed at the bottom and sealed. Any penetrations going through that need to be sealed. And then obviously any external doors, windows would have to be sealed as well. Totally closed and latched for the purpose of the test. So when we look at sealing some of the equipment, one of the primary pieces of equipment we're looking at here is the in-suite HRV systems. So they're using a Zender in-suite HRV system, which has, as Sandra pointed out earlier, has some external ports which go to the exterior of the building with an intake and a supply. So there's several different ways we can seal this system up, and there's a primary way that we always recommend, and then if that's not possible, then we have other options. So the primary way that we would recommend sealing a mechanical system of this sort would be to seal from the exterior of the building. So this means the exhaust and supply ports that Ina had at the beginning of the video on the underside here, or on the exterior of the building here. And then a secondary option for that would be sealing actually at the HRV itself, so on the intake or exhaust ports. And then finally, if neither of those were an option, you could certainly seal at the actual register or grill itself. Now, the problem is when you do seal at the grill or register itself, you can introduce additional duct leakage into the air leakage testing. So for this reason, we always recommend primarily to seal from the exterior of the building. So you're not introducing any additional leakage, which could happen through the ducting itself. You're only including the leakage through the building envelope. The closer you seal to the exterior of the building, obviously, the less chance we have of including any of that into the testing. A good example of this is the hallway pressurization, which will be stored in this rooftop mechanical room here. We'll have an HRV located in here, which will be servicing all of the hallway pressurization ducting. So you could certainly seal this at every single duct terminal, but it makes more sense to seal this at the exterior ports, which will be located in here. And that's going to eliminate any of that additional duct leakage that we could potentially see throughout the entire length of those big long duct runs throughout the entire building.
I'll make a quick comment there if I could. So, you know, you might tend to think, or you might hear the mechanical contractor or the builder say, well, wait a minute, you know, we seal up all that duct work, you know, it's super tight, you know, we tape, mastic, everything. We totally understand that the ductwork is going to be at least fairly snug, but Travis's suggestion and sort of the caution that we've learned is the more our testing boundary includes the interior ductwork, depending on where the sealing is done, the more interior ductwork you're including, the more potential for that leakage. And as much as people say or feel that their ductwork is completely airtight, the reality is that it never is. And you know that as soon as you start doing some duct leakage testing, which we certainly have done. So it's just a precaution, again, particularly for a building like this. We know that it has to meet a very aggressive air tightness target. So we want to make sure we test in a way that gives the best chance for success. And Travis will quickly explain that, you know, it's not, you can't always practically seal it from the actual location of the air barrier, but that would be the ideal. If you can seal right up against the air barrier system, that would be ideal.
Yes, absolutely. Thanks, Joanna. Some of the other items that we would typically see in a suite that we would seal that you know, in a building that's not a passive house building would be other exhaust penetrations, such as like kitchen hoods or dryer vents. So these are items that are typically on our list of items to seal, mechanical ducted items. But because obviously for the appliances that we're using in a passive house building, we're using charcoal filters in the kitchens, we're using condensing dryers, everything's ductless to the exterior of the building. So we're not having to worry about sealing any of the extra equipment, which is always nice to reduce the list. However, we still have to make sure we seal things like plumbing, any P-traps, stuff like that. They have to make sure that these are primed and because we can get, you know, airflow coming through. And any floor drains that were happening in any mechanical rooms or anything like that are part of the testing area, testing boundary. We certainly want to make sure that those are primed also, so we're not introducing any additional air leakage into the system. So typically, I guess I could talk a little bit about the testing procedure itself. Something like this documentation is standard for E3 to produce for every test that we do. But leading up to this, we would actually have several meetings with the consulting team to discuss, you know, the air barrier or how the building is constructed, looking at the construction schedule. And then we would plan a site visit for for myself or Ina or some of our field technicians to come out on site there and actually do a walkthrough of the building so we can familiarize ourselves with these mechanical systems, with the building layout, particularly with a building like this where we're looking at having difficulty interconnecting spaces, interior spaces. And then once we've done that site walkthrough and had a talk with the construction consulting staff, we generate this document here. This is a air tightness test plan and building preparation for the test. And this would be tailored for the specific building that we're testing, and including the correct testing standard that we're testing to as well. Once this documentation has been viewed by the construction staff and everyone has an understanding of it and all the questions have been answered, and the testing time has been scheduled in, we'd actually have a member of our staff would go to site the day before the test, just to ensure that everything has been sealed up in accordance with our expectations, to make sure that there wasn't any hiccups, that the building is ready to be tested the following day. And then it just makes the testing, time to do the actual testing itself a lot quicker. The test itself is not a tremendously long period. We generally allow 2 to 3 hours to do a building of this size, certainly in that amount of time. But I'm sure, like Ina always says with this, he always has an analogy that it's like painting, it's like 90% preparation, 10% actually conducting the test. So I think that's very apt for the testing procedure. I think it's all comes down to how well the building is prepped. The more time you spend preparing the building correctly, the better the test will go and the more accurate the data that's gathered will be. So part of this testing documentation, we give a quick little checklist here that the construction staff can use to go through, as well as all the imagery that we have of the site-specific photographs. And that's typically it. Ina, is there anything else that you'd like to add in that I might have glazed over there?
No, I think you caught everything. The main takeaway that we've certainly have learned over the years is it is a lot of prep work. And it's important to, I think, realize what you're getting yourself into when you look at this testing. And as Travis said, the actual process of running the test is very short. All going well, it's only going to take a couple of hours to run the test and get the numbers, but it's hours and hours, and in fact days, and over a couple or more months, where you have to start getting prepared and do at least a couple site visits and collect the mechanical drawing information, have discussions with the site super to get all these things lined up. So it is a surprising amount of prep work in order to have a relatively quick and successful test.
Okay, I will stop the sharing there, but certainly happy to answer any questions that anyone might have around the testing procedure, building preparation, or anything around that. If anyone has any questions around that, we'd certainly be happy to answer those.
That's a good question, Travis. Did you happen to have time to do a calculation for how many fans?
No, I didn't yet. I haven't done a full calculation for that yet, but I think we're looking at, I would assume, based on the size of the building, that it's going to be 2 fans, a double door fan set in the front entrance of the door. Yeah. Yeah, that I'd have to calculate that, but for sure, just because we're making assumptions on how airtight we think this building is going to be, I certainly think that we wouldn't need more than 2 fans.
It is one of the nice things about testing passive house buildings, even relatively large ones. You don't need a lot of fan power compared to typical buildings. So that's actually quite nice in terms of being the testers who have to mobilize and operate that equipment on site. I believe we only needed one one high-powered fan to do the air tightness testing at the Fraser Street Passive House building. So if anybody in the audience happens to be familiar with that project, that is not a very small building, but it's tight enough because it's built to Passive House standards that only required one, albeit high-powered fan, but just one. That was pretty cool to do the testing in a building that size with just one fan.
There was a couple other questions, but I think they sort of got answered. But anyone that's not following on the chat,
Oh, yeah.
there was, yeah, I think one was answered just earlier, like in the conversation. But I think it's an interesting conversation on this, the leaving holes between units essentially on each floor, which you've done, and then Scott Kennedy followed up with sort of an idea. It's the same issue on townhouses. Was it can be like, is that a strategy that we take in early phases and build it into a design that has something that would then, with a grill or something, cover up? Which I think is an interesting concept to think about in this. The requirement for air testing is critical, and then also you have to fix the world. So
I think it's a very smart idea. I mean, it's just a different thing. I mean, there's no reason why it needs to be a weird idea. Obviously, everybody realizes in the end, the integrity of the fire barrier and the party wall has to be back in place. But as soon as you start understanding the reality of blower fan testing, and again, particularly with something like townhouses, it's even a smaller building. So you have less leeway for a few extra square inches of leakage here or here or here. So, you know, when you do a bunch of this testing, especially if you're trying to hit a tight target like Passive House, you really want to stack everything in your favor. And we think it can be a very advantageous way to have the site people put a little more work into putting some holes in those party walls and then having to patch them up, rather than that cost going towards us doing a much more elaborate and potentially less accurate job of testing the building.
yeah, it seems it's an interesting path of least resistance.
Yeah.
Well, we actually did bring it up from the beginning that we will have to have those holes, right? So it wasn't a surprise to the contractor.
The other one that I think it gets away a little bit from air barrier testing, but Eric had a question on the 2-floor townhome units requiring only the one ComfoAir 200 per unit. What do you know the square footage of those units, Sandra? I know I'm putting you on the spot on that, but it's probably
out of the top of my head, no. Scott, do you know? Simon, maybe? I don't.
I mean, it's probably governed by the fact that you've only still got 2 bathrooms, right? So that's really what 2 bathrooms and a kitchen are really. The exhaust typically is what governs the amount of air you need. So it'll be stretching at 200 right to its limit, but I think it's possible to do it.
It is possible. We're doing it. It is kind of, it is stretching it. It was kind of at its, not at its limit, but certainly
it's pushing its capability. But
it's pushing it. I'm trying to find the area, but I don't think I'll find it.
And those 4 sand, I know we're getting into mechanical systems, but the 4 sand in tanks, which Scott, you clarified, is the 1 gal G3s for the entire building. That seems really impressive to me.
Well,
No, you've got, there are
3 now.
using G3s, but we're using 4 119-gallon tanks with G3s, plus a 5th tank, which is a swing tank that's electric resistance for the recircling.
Nice. Nice.
That's true. Through the presentation from Sandra, as she was going through the building sections, and I noticed I'm not sure, was the air vapor barrier, which was installed on the inside, did it cross to the outside between the floors? Or I,
Yes, it did. It did. Let me open that presentation again. That was the part with the floppy bit. It's 1 second. I'll find.
Yeah, I think it transfers out through we'll throw it out to the sponsor to see the my address goes on the outside of the floor truss.
Yeah, the air barrier does, but then to keep the vapor control layer on the inside, we actually elected to shoot 2-pound
Spray foam box ends.
spray foam on the inside. So the vapor control layer is still on the warm side.
well, that was exactly my question. Because the line simply jumped to the outside, which makes, if it was still the vapor barrier, it would be on the cold side.
Yeah.
And your vapor would be able to access the building material on that warm side where your dew point is definitely going to be there. So if you treated that with spray foam, was enough thickness of spray foam, so you transferred your vapor barrier further in, and you shouldn't have that problem. But I didn't notice the spray foam part, or at least it was not mentioned through the conversation.
Hey, Chris, sorry. Thanks for doing this again. Just a quick question that I wrote in the chat. Is there a rule of thumb for air testing multifamily buildings, or does it depend entirely on building typology, number of stories, etc.?
I would say it's always the same basic principle. There will be differences depending on the testing standard. So there's differences, even the volume of conditioned space between passive house and other testing standards. Some testing standards require both pressurization and depressurization. Some require just one. Some require different levels or different maximum levels of depressurization or pressurization. And not so much maybe on the Part 3 building side, but on the Part 9 building side, there can be even differences with how you prepare the building. So probably the first rule of thumb is to be very, very clear what are the intricacies of the particular standard that is supposed to apply to testing that particular building. That's probably the main thing, and that's sort of confusing enough. So if you can survive that, then that'll go a long way towards understanding how the building should be prepped, how it should be tested. We do a lot of testing, not just for passive house buildings, but for everything from a laneway house to high-rise condo buildings to meet step code, for example. So anybody has any questions or wonders about something, or is looking for a air leakage testing company to test larger, more complicated buildings, please do reach out to us.
Awesome, thank you.
I do want to thank Travis, Einar, and Sandra. It is a really interesting project, and I think that preloading of that size of building and air test it does take a lot of thought and knowledge, and I appreciate you guys sharing to the group that knowledge and wisdom as hopefully there's a lot more of these kind of buildings built.
Yeah, we appreciate the opportunity to share. I mean, we've been super excited about being involved in buildings like this and learning the things, and you know, we nerd out about it the same as you guys do. So it's, you know, we're kind of a kindred minds, and we're also aware that you know, some or most of the audience, you're going to get into this in your own building or looking at engaging a company to come and do this testing. So we're happy to share some of the things that we've been learning from our experience that might be helpful for the group here. And Chris or Sandra, you might be mentioning it anyways, but we're excited about, you know, the opportunity of revisiting this building when we've done the final test and talk more about the final testing procedure and what kind of results and maybe if there's any need for air leakage inventory work, what the results of that are as well.
Yeah, I think the idea is to actually document while we're testing.
Yeah.
That one is not that easily staged after.
Yeah, the idea was to make this a bit of a part one in a loose series within these socials that we can apply. We've sort of seen what the preemptive work looks like, and then what is the effect of it in the post with a good team involved. Expectation there, and then also if you don't hit it, what are the tools that are there to meet those marks, which there are a number of those available. So it's kind of a full piece to see this project through. In the place where we can't, normally we get to tour and walk around these parts and sharing this wisdom, and these days under COVID, that's not as possible. So we do our best through Zoom. That's what I would say. So if there's nothing else, I'm happy to cut this one off, and I appreciate everyone for sticking through this. We had pretty good presentation and numbers here. So with that, I think I'm going to say good night. A little early.
Everyone.
Thanks, everyone.
Thank you very much.
Good night.
Night.
Thank you. Good night.